Good morning, sir.
Very good morning to all. As our routine Saturday practice, we are having one another very important topic today related with ultrasonic methods for non-destructive testing and evaluation of materials. We have with us Professor Dr. Yudhishthir Kumar Yadav. He is an ex-CSIR National Physical Laboratory Scientist. He is MSc from MD University Rohtak, MS and PhD in ultrasonics, NDT from BITS Planning. He is a former principal scientist at Acoustics and Ultrasonic Metrology Section, National Physical Laboratory, New Delhi. He has more than 150 research papers in national and international journals and conferences. He is a life fellow of USI, ASI, MSI, and ISNT. He is former General Secretary, Ultrasonic Society of India, and Publication Secretary of the Journal of Pure and Applied Ultrasonics, run by USI. He has research experience of more than 40 years in the field of ultrasonic NDE, ultrasonic power measurement, transducer design, and ultrasonic output measurements and standardization. He designed and developed ultrasonic NDT techniques and ultrasonic power transducers on behalf of CSIR NPL. He participated in BIPM key comparison on ultrasonic power measurement efficiency testing program in ultrasonic entity and APMP key comparison in low frequency vibration measurements. Thank you very much, sir, for accepting our request and delivering a talk on this very important topic, which is related with for the testing of materials. It is very good, sir. I hope that our laboratories and the industries will be benefited from your lecture. Thank you very much. We have with us our Honorable Shri B.N. Dixit, our Director Legal Metrology. Sir, certainly you are always a torch bearer for us, giving us the path and the direction where to move and how to move. So we are always looking towards you, sir, for the motivation. Thank you very much, sir, for joining us. I would like to request you to kindly speak few words on this workshop and bless us. Thank you, sir. Over to you, sir. Dixit, sir.
Okay. Very good morning, Sri Ashutosh Agrawal ji, Director Legal Metrology, Government of India. Dr. Yudhishthir Kumar ji, the senior scientist and professors and so many designations and research work and Dr. Ashutosh Agrawal has told a lot of the things about you, and I think we are also having the good and background of the National Physical Laboratory. And today topic is very important, and I think it is related with your subject that without destructing the materials, how it will be evaluated and how it will be tested. So metrology plays the very important role for the measurement of the standards, equipment, and so many other things. While testing of the materials, also the various equipments are necessary for the measurement of the various parameters. And for the testing of the materials, there may be the different standards. So from those various standards, I think one of the standards will be from your side on which you might be speaking, and we are very eager to know about that. What is your lecture and what we are and the peoples who are participating in these very programs, they will get the good knowledge on the new subject. So I hope for the success of the programs, and I wish that we'll get the good knowledge and acknowledge your knowledge and background and all those things from this very lecture. Thanks, and I wish for the success of the programs. Thank you, Ashutosh ji. Thank you, Dr. Yudhishthir Kumar ji.
Thank you, sir. Thank you very much for your kind and motivating words. Thanks a lot for being with us. Thank you very much, sir. Thank you. Now, I'd like to request Dr. Professor Yudhishthir Kumar to kindly enlighten us with his vast knowledge and experience. Sir, I would like to request you after this program, this whole video will be available on our website. as well as this PPT will also be available on our website so that the participants can get the knowledge and the information at any point of time after the program also. With your kind permission, sir.
Sure, sure.
Thank you, sir. Over to you, sir, please. Thank you.
Thank you, Dr. Ashutosh Sagraji. Honorable Dr. B.N. Dixit, former Director, Legal Metrology, or most respected Dr. Ashutosh Agrawal, Director, Legal Metrology, and convener of this national workshop. All the team members of the Legal Metrology workshop, for today's workshop, distinguished participants, a very good morning to all of you. The title of my talk today is Ultrasonic Methods for Non-Destructive Testing and Evaluation of Materials. So, this slide shows the beautiful photograph of the front side photograph of the National Physical Laboratory, one of the reputed research laboratory in India under CSIR, Council of Scientific and Industrial Research, CSIR. It is National Meteorological Institute of India, which maintains primary standards for all the physical quantities, and it is a prime lab for research and development in material sciences in vast area of basic sciences. In our field, it provides calibration facilities for ultrasonic equipments, whether it is NDT equipments or medical equipments, ultrasonic devices, and maintains primary standards on ultrasonic power measurement, which is basically essentially required for ultrasound scanners and medical diagnostic equipments. Now, coming on to the next slide, you all must be knowing about acoustics. As you know, acoustics is the study of mechanical sound waves and a wide range of frequencies. On the basis of frequencies, it is classified in three categories. Infrasound, which has 0 to 20 hertz frequency. Audible sound, which usually we use, this is from 20 to 20 kilohertz. And ultrasound. Ultrasound means beyond sound, or sonics beyond means sound. So beyond sound, which we cannot hear, that is ultrasound, and that consists frequencies of more than 20 kilohertz. As for example, we see for ultrasound we see the bands, and we can generate it using piezoelectric crystals. Infrasounds, you must be having observed the earthquakes, and very low frequencies sound are generated. And audible speech and music are the examples of the audible sound. Now, metrology in ultrasonics. Metrology in ultrasonic refers to the science of measurement involving the use of ultrasonic waves to determine properties of material, dimensions of the object, calibration of ultrasonic devices. Ultrasonic involves the use of high-frequency sound waves for various applications, including non-destructive testing and evaluation, thickness measurement, medical imaging, cleaning, ultrasound therapy, and in high power ultrasonics, it's also used in cutting, drilling, and welding. It is commonly used for NDT, which is detecting a defect or flaw or any inclusion in the test object. And ND refers to non-destructive testing after detecting the locating and sizing of the defect or flaw or any inclusion in the test object. In importance of metrology in ultrasonics, it is important to accurate measurement and calibration. All are crucial in ultrasonics to ensure reliability and consistency of results, safety of any equipment and personals who are operating and who are under test during this use, and compliance and with regulatory standards, optimization of ultrasonic processes, quality control and assurance. Key aspects of metrology in ultrasonics are accurate measurement of frequency and wavelength, then ultrasonic measurement, longitudinal wave, transverse wave, and surface wave velocity for quality determination of flows or any inclusion, and evaluation of materials it is used, and power and intensity to ensure safe and effective operation of medical and other equipments. Transducer calibration is to ensure accurate transmission and reception of sound waves. Distance and depth measurement used in ultrasonic imaging and testing applications. Ultrasonic field characterization that use measurement and mapping of ultrasonic field for optimized performance. Application of metrology in ultrasonics, it can be classified that in the NDT, in medical imaging and ultrasonic cleaning, cutting, drilling and medical therapy, then material characterization, industrial process controls. By ensuring accurate measurements and calibrations, metrology plays a vital role in the development and application and safety of the ultrasonic technologies. So, ultrasound has wide range of applications, and like in medical diagnostic and therapeutic applications, in biotechnology and microbiology, in pharmaceuticals and cosmetics, in petrochemistry, in civil engineering, ultrasonic characterization of media like fluids and emulsions, nano and microparticles, dispersions, soft materials, porous bodies, and inhomogeneous materials. In high power ultrasonics, that can be used, ultrasonic can be used as drilling, cutting, soldering, helpful in welding, emulsification, homogenization, crystallization, dewatering, degassing, deforming, particle size, reduction, extrusion, and viscosity of alteration, ultrasonic therapeutic use, and many more. For low power applications, high frequency, low power applications, usually ultrasonic NDT is used. It is used for NDT of materials, for detection, location, identifying the defect, and then afterwards sizing of the defect. What we see in the applications of the ultrasound, that mainly three parameters: ultrasonic power, ultrasonic attenuation, and ultrasonic velocity are measured. So we will be emphasized on ultrasonic attenuation and velocity, which are mainly used in ultrasonic NDT of the material. Now, if we see the basics of the ultrasound, ultrasonic velocity can be defined or evaluated by the product of wavelength used and frequency of the ultrasound waves, or it also can be distance traveled by travel time. In usually what we have seen that in gases, the ultrasound velocity is less than 1000 meters per second. In air, it is 330 or of that order. Liquid gases, in liquids, it is 1000 to 2000 meters per second. In polymers, 2000 to 3000 meters per second. Concrete, it is 3000 to 4500 meters per second. In metals, it is 4500 to 6500 meters per second. Usually in steel, mild steel used, maximum used applications and having calibration blocks also, it has 5900 meters per second. Ultrasonic attenuation can be defined as transmission amplitude and received amplitude ratio of these two amplitudes, 20 log of the ratio of this amplitude in decibels per meters per or in other units it is used in amperes. And acoustic power can be derived by mgc. M is the mass of the transmitted signal, acceleration due to gravity is the g, and c the ultrasonic velocity in that material. In non-destructive testing, usually we use 20 kilohertz to 25 megahertz frequency transducers with few milliwatts, means low watts. Ultrasonic cleaning is used with very low frequency and high powers, 1 watt to 100 watts even. Medical diagnostics, low power and frequency from 2 megahertz to 12 megahertz usually. In medical therapy, use low frequency and high power, 1 watt to 20 watts. Measurement in ultrasonics is important uh, as it directly affects the accuracy of various applications, including NDT in medical imaging, material characterization, industrial process control, and type of velocity measurement. Longitudinal wave velocity, which measures the speed of sound propagation through the material. Shear wave velocity measures the speed of shear waves which travels perpendicular to the direction of propagation. Surface wave velocity measures the speed of surface waves which travels along the surface of the material. Velocity can be measured by measuring the time of flight. Time taken for an ultrasonic pulse is measured traveling through the material. And phase velocity method, this measures the phase shift of an ultrasonic wave as it travels through the material. And frequency domain method measures the frequency shift of an ultrasonic wave due to velocity changes. Number of standards are there, like International Standards Organization, ASTM standards, NIST standard, IS standards. There are a number of standards on calibration and measurement of the velocity. Usually, ultrasonic flow detector is used for measuring the velocity and detecting the defects. Ultrasonic thickness gauges are also there. Phase array system are also available in advanced phase. Challenges and limitations. Material variability is one of the challenge. It changes the material properties which affect the velocity measurement. Temperature effect or temperature changes impact velocity values. Instrument calibration, ensuring accurate instrument calibration, that is also a challenge. Recent advances, high frequency ultrasonics, it increased resolution and accuracy in detection of the defects. Phased array technology, it improved imaging and inspection capabilities. The machine learning algorithm, it enhanced the data analysis and interpretation. Now, ultrasonic attenuation. As I saw that 3 parameters basically are important. So ultrasonic attenuation, what actually it is loss of acoustic energy due to diffraction, reflection and refraction, loss of energy due to scattering and absorption. Ultrasonic attenuation can be further classified in two parts, apparent attenuation and true attenuation. Apparent attenuation is usually what we measure, that is the loss of acoustic energy and is measured to compare the material characteristics. True attenuation, whereas it is combined effect of scattering and absorption. It is uniform for a material at a certain frequency throughout the ultrasonic field, and it is characteristic property of a material. We can find out using measuring this, you can find out the material characteristics in a finer way. Though ultrasonic attenuation is difficult to measure, as the result includes other loss mechanisms like beam spread, field effect, couplant mismatch, transducer bonding with the test object, sample geometry, and which are very difficult to isolate. And we have to take care most of these factors in account. Then scattering is energy which depend on relative magnitude of wavelength and average grain diameter, and it increases with increase in diameter. Absorption, usually after absorption, mechanical energy is converted into heat, and ultrasonic attenuation is used in characterization, sizing of the defect using DGS, distance gain size, or DAC, distance amplitude curve diagrams. It predicting the grain size tensile strength, yield strength, crystal damage, and fatigues. As I earlier told that ultrasonic attenuation is the reduction of ultrasonic wave amplitude as it travels through a material due to absorption, scattering, and diffraction. It can be measured as a transmission method, which it measures by comparing the transmitted and received signal amplitudes. And reflection method, which measures attenuation by analyzing reflected signals. Pulse echo methods, which measures attenuation by analyzing multiple reflections. Usually, for evaluating the ultrasonic attenuation coefficient is measured and measured in decibels or Nepers. Attenuation rate can also be derived by measuring attenuation per unit time. Usually, ultrasonic flow detector, ultrasonic thickness gauge, phase array system, or ultrasonic attenuation meters are used for measurement of these equipment, this attenuation. And there are a number of standards, Indian standards and international standards available. Again, this slide shows the ultrasonic applications of on attenuation, that is NDT, and evaluation of material, sizing defects using DGS and DAC diagrams, predicting gain size, tensile strength, yield strength, crystal damage, fatigue. In addition to this, it is used in food products, the age of eggs and potatoes, ripeness of fruits, fat content in beef, and percentage of solids in milks. And generally, these tests are both non-destructive as well as non-contaminating. So, in so many applications, the ultrasonic attenuation measurements are used. Ultrasonic velocity, it has various use, like in study of physical properties of the matter, study of chemical properties of the material, various elastic parameters can be determined by using measurement of longitudinal velocity and transverse velocity, transfer wave velocity of the material. Other features such as porosity, strength, inhomogeneity, anisotropy, density, corrosion, elastic contents also can be determined by measuring ultrasonic velocity in longitudinal as well as in transverse wave form. And the velocity is also used for thickness measurement, for non-destructive testing in detection, location, and size of the flows. Ultrasonic velocity parameters used. So, what is NDT? Usually, non-destructive testing and testing is you can define it in the way that it is to inspect or measure without doing any harm to the subject material, or use of non-invasive techniques to determine the integrity of a material or components or a structure, or quantitatively measure some characteristics of an object without harm. In addition to ultrasonic NDT, there are some number of methods, NDT methods, that is liquid penetrant testing. It can be used for subsurface defects. Liquid penetrant and developer powder are used for surface indication. Magnetic particle inspection for surface defects and ferromagnetic materials using magnetic field. Eddy current testing, it uses electromagnetic induction to detect and characterize surface and subsurface flows can be detected by using this. Radiography, use either X-rays or gamma rays to examine internal structure of the material. And acoustic emission, it uses the release of ultrasonic stress waves to identify defects in material. The ultrasonic wave originate from within the material to being inspected. And ultrasonic test UT, it uses high frequency sound waves to conduct or evaluate the test piece. Ultrasonic non-destructive testing, or NDT, or non-district testing and evaluation of the material. It uses high-frequency sound waves from 0.1 megahertz to 50 megahertz to inspect materials for internal flaws like cracks, voids, or corrosion, and measure material properties without causing any damage. Techniques involve transmitting pulses, returning echoes from reflectors, flaws, or boundaries to a transducer for signal analysis. There are various ultrasonic entity techniques used. One is mainly used is pulse echo method, which uses a single transducer, or we can also say transducer as a probe. Single transducer is used for transmission as well as the reception of the signal and analyzing the defect. Through transmission method, this uses separate transmitter and separate receiver probe on opposite sides. A decrease in received sound intensity indicates a flow. Phased array ultrasonic testing employs multiple transducers to shear, focus, and sweep beams, producing detailed cross-sectional images of the internal structure. Another technique is time of flight diffraction. It measures the time taken for sound waves to diffract around the tips of a flow, and it offers high precision for fly sizing. And guided wave testing, it is usually used for low frequency sound waves to propagate along pipes or structures, ideal for long range inspection or inspecting through insulation. Soundness of material, of making a sound also is used for defectness or defect of the material. Then acoustic emission. So NDT and NDE may be applied for, this slide shows, for materials to detect, locate, and size the defect, flaw, cracks, voids, or inclusion. Porosity in materials like metals, plastic, and composites. Thickness measurement with one side surface SS. Material characterization assessing grain structure, elastic modulus, and hardness. Industries used in aerospace, automotive, manufacturing, and construction for quality control and structural health monitoring. We can compare the material with standard sample given using ultrasonics. We also can compare the surface finish of two or more materials, then parallelism of surfaces and perpendicularity of the surfaces can be adjusted. Ultrasonic testing is highly sensitive and allowing for deep penetration into materials to detect and very small defects. The choice of method depends on various factors. First is the type of material to be used, whether it is porous, metal, wood, or whatever it is. It depends on the material to be tested. Then shape and size of the object accessible to us, and accessibility, whether it is accessible from one side or both two sides of the test object. Then testing conditions, environmental conditions, whether it is hot or cold, or other environmental parameters also affect the test defect determination. Requirement of online continuous or monitoring, whether you want to test the object at the online or offline, and you want it continuous monitoring or instant monitoring, instant test. Then economics, whether it is a costly affair or and the type of defect, whether it's lateral or axial, which type of defect it is. No, we come to detect a defect. The equipments required for ultrasonic flow detection are ultrasonic flow detector, ultrasonic transducers, or we also call them as probes, calibration blocks, and couplant. Couplant is used to transmit the ultrasound waves smoothly from the transducer to the test object. Calibration blocks, which are the reference blocks and used to set up for a particular application. Now, generation of ultrasound, we use mostly piezoelectric transducers, and they use piezoelectric effect. Most commonly used method for generation and reception of ultrasonic waves is by using piezoelectric transducers or EMAT, electromagnetic acoustic transducer. By using piezoelectric crystals, this slide shows the sample how the piezoelectric effect works. Suppose this is a quartz crystal, and using a DC battery, we apply a electrical volts to the piezoelectric crystal. So what we see, the crystal gets thicker. Crystal gets thicker due to distortion of the crystal lattice. If we change the polarity, of the to the crystal, what we see that effect inverses. So if we apply the AC voltage, if we apply alternating voltage, which generates crystal oscillations at a frequency of what we give, at a frequency f at which we are supplying it to a voltage. So the sound waves at sound frequency or ultrasound frequencies is given to the crystal to emit the sound waves. So in the piezoelectric effect, usually in ultrasonic entity, a short voltage pulse, high voltage, short duration pulse, high voltage generates is given less than 1 microsecond duration, and it given to a crystal, whether it is piezoelectric PGT or quartz or any piezoelectric of any material. It generates oscillation at the crystal's resonant frequency. Short duration, high voltage pulse is given to the piezoelectric crystal, which generates high frequency at the resonance of the crystal. This is usually shows the principle how ultrasound is generated through a PGT transducer. These are the photograph of portable ultrasonic flow detector, handheld ultrasonic flow detector, usually available. These are type of transducers. These requires frequency, bandwidth, and focusing to optimize inspection capability. There are 3 types of transducers: contact type, immersion type transducers, and element transducer. In contact type transducer, handheld manipulated ergonomic design, replaceable wear plates. Their wear plates also can be replaceable. Coupling materials of water. Coupling material usually used for these transducer is water, grease or oils, or any commercial available materials are used to remove the air gap between the transducer, and so that ultrasound is transmitted into the test object smoothly. Immersion transducer are designed to operate in liquid environment or in immersion testing, and all connections are watertight. So these are the cylindrical focus transducer, can be used in the water, spherical focus transducer, and dual element transducer is used for subsurface defects. This contains 2 independently operated elements in a single housing, one of the elements transmits and other elements receive the ultrasonic signal. One is element this, another element is this, and in a single housing, for detecting subsurface defects, so this is used. Here is the construction of probe, how a transducer is constructed. This is straight beam or contact beam transducer for transmission of longitudinal waves. This is the element, crystal, socket arrangement, and this is the faceplate. A backing is, or damping or backing is required so that it don't interfere the received signal back to the crystals. Similarly, the dual transducer, TR probe or dual transducer, there are two different elements. One is this and this, and it also have a delay block in front of the crystal. This is the angle beam probe or angle beam transducer. This is used for getting the surface wave transmission. This is a electrical connection. This is the element. This is placed at a wedge-shaped block, and normal beam or longitudinal beam is transmitted into the block, and it is at a certain angle. It's mode converted into the shear wave, and it emits at a certain angle. Shear wave is transmitted into the test material so that we can read the defect by using surface wave transducer. Then comes the calibration blocks. Usually these blocks are reference standard blocks, and these are named calibration block. These can be traceable to test laboratories for calibration of these blocks. In ultrasonic testing, various type of calibration blocks are used for setting up of the ultrasonic flow detection system and for different applications like V1 IIW V1 block, V2 block, step wedge, resolution block, distance amplitude curve blocks, distance gain size diagram blocks, flat bottom hole blocks, and so many. Let me show the diagrams of these. This is IIW V1 block. This block was designed and started by International Institute of Welding and given name of V1 block. This is used for setting up of the system for testing different ranges. This is 100 mm and 10 mm thickness. Various notches, artificial notches and thickness are made to set the system setup for different measuring range. This V2 block, similar type of application, but for setting up of the ultrasonic setup, test setup for small range, like 5 mm or 10 mm thickness block measurement. These are resolution block. A setup when we want to use it to resolve two defects very closely, use resolution block, so that we set up, we evaluate, or we use this. We confirm whether our system is able to resolve these two blocks or not. Able to resolve these blocks or not. So resolution block is used. Step wedge. These step wedges are in the thickness of 2 mm, 2 mm, 4 mm, 6 mm to 10 or 12 steps, and 1 mm to 10 mm thickness, increasing thickness steps. These are also used for the dual probe or dual transducer setting up of the setup for detecting subsurface defects. This is the distance amplitude curve block. This has various side drilled hole. This block has various side drilled holes, and these drilled holes are at same diameter but at different depth, and so that distance corresponding to distance echo amplitude is measured, and a graph is prepared. That will be a calibration graph for the different depth at for particular diameter of the side drill hole. And this is the flat bottom hole blocks. These are set of 19 or 20 number of blocks, and it is giving the dimension in such a way that it is cylindrical, diameter 50 millimeter, depth 19 mm, and here it is for 1.2 millimeters. The diameter can vary 1.2, or it can be for 3 mm, 5 mm, 7 mm, 6 mm, or 0.5 mm. This whole diameter can be varied, is varied in response to the application we require, and this depth of the hole also can vary. This is the ultrasound path when use it. We place the transducer over here, and we take a signal response from the flat bottom, and this is the depth of the ultrasound waves which it travels. So we using these flat bottom holes, FBH blocks, number of set of blocks, we plot DAC curve or DGS curve. DAC curve means distance amplitude curve. If the depth is varied and hole diameter is kept constant, so it will give us DAC calibration curve for testing a small setting up of the test. Usually, let me explain about the problem where these blocks are used. When we, after detection of a defect, when we want to size a defect, so it is easier to size a defect when the size of the defect is larger than the beam diameter. Transducer beam diameter, when the size of the defect is larger than transducer beam diameter, it is easy to size the defects by using 6 dB drop or 20 dB drop method. But when size of the defect is lesser than the beam diameter, what we measure is only the beam diameter and not the size of the defect is measured. So it is very difficult to measure the size of the defect, which is smaller than the size of the beam or beam diameter. So for that particular applications, these DAC and DGS blocks are used, and a DAC calibration curve or DGS diagrams are made for that particular application for a particular material. And echo response from what we receive, the echo response from the test object from that defect, that is compared using that DGS diagrams to estimate that this may be the size of the defect. So these blocks are used for making and getting the calibration curve for the DGS diagram or DAC diagrams. So this slide shows the use of ultrasonic transducer. How does it is being used? This is a contact transducer directly in the contact of the test material. A couplant is used, whether it is water, grease, oil. In the this is the photograph for direct contact testing. This is for immersion testing. Here a container is filled with water. This is the test material. This is the transducer immersed in water, and here water works as a couplant. This the sound path ultrasonic transducer is placed here. It transmits ultrasound waves into the material. The sound waves is reflected either from the back wall of the test piece or any defect inside it. It can come after reflecting from the defect or from the back wall, what we call it back wall. So we can receive the back wall echo as well as defect echo in response to the size of the defect. Here we see what we see on the flow detector screen, or there is a pulsar in the ultrasonic flow detector, and an electrical signal is transmitted to the transducer. Transducer converts it into the ultrasound waves, and ultrasound waves is through a coupling material is transmitted into the test material, and test material's sound waves after reflection from the back wall, back surface of the test object is received back to the transducer. So here this one is the initial echo transmitted to the transducer, and this one is the echo received from the back wall surface of the material. Here you see, suppose there is a defect into the material, so we will also receive the reflected signal from the defect. This shows the reflected signal from the defect or defect echo. This is the back wall echo. Back wall echo, we say the echo received from the back surface of the test object. This is the way how through transmission testing is performed. In through transmission, there are two transducers, one as the transmitter, another as the receiver transducer. If there is no defect, the initial echo is here, and the received signal is slightly reduced due to the attenuation into the test material. But when there is a defect inside it or flow inside it, so what we see that there's much more attenuation is there, or the defect is the ultrasound is much more attenuated. So this number two, this is the reduced signal. If we compare the normal sample to the defected sample, so we can assume that this is the defective. There is a defect, and we can size it by other method. This slide shows direct contact method. Direct contact method using dual element, using fixed delay method. This is the ultrasonic transducer test object, dual element. When the sample size is less, we use it, and sometimes we also use a fixed delay is used for the ultrasonic testing of the object. Then through transmission, two transducers are used. This is a comparison of direct contact dual element, direct contact single element or pulse echo method, this direct contact fixed delay method, and this is through transmission with using two transducers. Again, immersion testing use single transducer is the test material. So it is a comparison, or the slide shows the comparison of all these methods and used for different applications. In immersion testing, how the echoes are observed. Suppose this is the immersion testing setup. Water is this. Is surface sound intensity. Sound is transmitted into the material through the water. So, and here it is in defect. Second position, it shows the material, the water as a coupling material, test object, and this test object is having a flow, a defect into it. So how the echo is reflected. This is the initial pulse, interface echo from here inside the water and test object interface. This is the back wall. Back wall means back surface of from the back surface of the test object. And if there is a defect, so what we see that between interface echo and backwall echo, there will observe another echo, that is from the flow flow or the defect echo. So this is the immersion testing, how we will visualize the different echoes. This is the photograph of a micro porosity by normal beam probe. This is a normal beam probe, and some micro porosity is available in the test object. So this will show this type of result. This our screen will show this is the backwall echo, initial echo, and this type of signal is for porosity, response from the porous material. This is defect detecting when the defect is not lateral, it's axial at some angle. So by using the normal beam probe, it is not much more identified or having some problem. Then we use shear wave probe or angle wave probe. This shear wave probe transmits the shear wave sound at a certain angle to the block. This block, after the reflection from the back wall, strikes to the defect, and this echo is observed. This is the surface wave probe. Surface wave probe usually moves on the surface. These are partly shear wave probes, and if any defect is there, we receive an echo from the defect. This is the system for plate testing. Suppose plate, because it is very not comparable to bigger object. If the plate testing is there, some slight laminations are there. These are the observation of the delamination. This is the initial pulse, this is the backwall echo from back side, and this is the flow echo. Again, it is a second backwall echo and second flow echo. We can also use it for testing of welds. Suppose the weld is not properly welded here and it has a lack of fusion. So we can determine the defect, as well as we can locate it by using the signal. We have seen that this is the flow echo. Angle beam probe is used, and suppose this is the angle of the probe is the beta. Sound path transmitted to the surface to the defect is S, and surface distance is A. Reduced surface distance from the center of the transducer. So reduced surface distance is A dash, virtual depth is D dash, then D is actual depth of the defect. So we can, using this relation, we can determine the depth of the lack of fusion defect or defect in the welds. So it's commercially usable and very useful for determining the lack in the welding applications. This figure shows the thickness measurement or pipe testing. Thickness of the pipe or any defects can be related by using this. So this is the thickness, 2 to 4 mm thick. If thickness varies, the distance or time varies. So no, these are the earlier we have studied, seen that how we can easily detect the defects. Now, how to size a defect? Key techniques for sizing defects are 6 dB drop method, half maximum technique. This how does it work? The probe is moved across the flow until the maximum echo amplitude available from the defect drops to 50 dB, 50%, that is minus 60 dB, 6 dB of its maximum value at a edges defining the edge of the defect. So by defining edge of the defect at 4 sides, that size can be evaluated. Maximum amplitude method is also there. The probe is moved to find the position of the maximum signal amplitude, which is then compared against the reference reflector, which are FBH, to determine the size. These maximum amplitude are used to determine the size of the defect, which is smaller than the beam diameter, where we use FBH blocks and DAC or DGS diagrams. Then 20 dB drop method. 20 dB drop method is used for more precise sizing, particularly for large smooth defects. By measuring the distance between the 2 points where the signal drops 20 dB from its maximum amplitude, we derive the distance. So the precise sizing can be available. And we can predict that this is the size by 20 dB drop method. Then calibration method. It uses reference blocks with the side drilled hole, notches, distance amplitude correction, curves to set sensitivity of a quantified defect size. That means the amplitude received from a artificially drilled hole or reference block, whole artificially made reference blocks, and response from that block is received for a particular identified defect of different size, like notch and this sided hole or flat bottom hole, and that test object defect is detected, and then amplitude test object defect is received, and that echo amplitude is compared with the reference block holes. So this calibration method is used in such a way. Then time of flight diffraction method. It is a highly accurate technique that measures the time taken for ultrasound waves to diffract from the tip of a crack to determine its size. It is, although it's cost effective, and but when some specific requirement is there to determine the defect exactly, then time of flight diffraction technique is used. So key factors affecting sizing accuracy. Usually size accuracy have various factors to which affects. One is the probe characteristics. Probe characteristics depends basically on the frequency, diameter of the probe, and beam shape. Beam and the material shape. Material properties, whether material to be tested is attenuating and scattering. So these are also the factors affecting the size of the accuracy. Then defect orientation, whether the defect is lateral or axial or misoriented flows, that may not reflect enough energy to be accurately sized. These are the problems when we use the ultrasound as an application for the size of the defect. This slide shows ultrasonic imaging. A C-scan image is shown, which gives high resolution images and can be produced by plotting the signal strength or time of flight using a computer controlled C-scan system. So this is the photograph of grayscale image produced using the ultrasound C-scan system. Sound reflected from the front surface of the coin. Sound is reflected from the front surface of the coin. And this is the grayscale image produced using the sound reflected from the back surface of the coin. Inspect the heads and sides. So there are two ways by which we can use the C-scan system, and we see that the sound reflected from the front surface shows the better image. Here we see this slide shows that ultrasonic technique developed for calibration of flat bottom hole blocks. Where at NPL we have performed the calibration of these flat bottom holes, FBH blocks, which are usually used for making calibration curves and for particular application of sizing of the small size holes. Here we have used a technique for and using ultrasonic itself. Otherwise, by other methods, it was time consuming and cost effective. The parallelism of the end surface, parallelism of this surface and this surface is compared by ultrasonics. Parallelism of anti-surface, this surface and this first surface, parallelism of anti-surface and bottom of the FBH, flatness of flat bottom hole. This flat bottom hole echo response shows the comparison of the flatness of this this hole. The technique is useful. Technique which we use to is for the calibration of set of DSC blocks for various materials is very useful, and it is taking less time to calibrate as compared to dimensional standards. This is the transducer. When we use a sizing the defect, we should have the transducer characteristics, what transducer which we are using. So this is the distance. This is the distance. This is the transducer, 5 megahertz transducer, 10 millimeter probe we have used, and by using this transducer, we have plotted a distance amplitude curve, typical distance amplitude ultrasonic response curve for using aluminum 7010 block of 1 to 1.2 millimeter flat bottom holes. These are the calibration curves for using the set of curves for measuring the size of the smaller diameter defects. These are the two graphs which also again shows the typical distance amplitude calibration graphs for ultrasonic response for bearing side bearing steel blocks. Earlier was the for aluminum blocks. These are the for bearing steel blocks for the same transducer. This is the again a similar calibration curve plotted for typical distance amplitude ultrasonic response curve for different alloy of aluminum for estimation of the small size defects. Here is an amazing iron pillar of Delhi. We have worked and studied the amazing iron pillar of Delhi by using ultrasonic methods. This is our team of experts. We in our earlier times in 90s or 85, 90s, we worked on the ultrasonic iron pillar near Qutub Minar, New Delhi. They are Dr. Ashok Kumar, Dr. J.N. Som, Sri Jagdish Lal Ji Sutha, Dr. Subhash Chandra, Om Prakash Ji, and myself are there, visible there. It is situated at Qutub Minar complex in New Delhi. It is 1600 years old and weighs about 6,000 kilograms. It is having a non-corrosive nature. Its longevity strength has amazed all the scientists the world over. Some people from metallurgy side, they have tested its composition by extracting the samples from the bottom side, which is submerged in the earth. But that is a destructive type of testing. We have performed the amazing pillar using ultrasonic NDT method to understand these reasons for its non-corrosive nature. The studies for the first time showed that the iron pillar has a heterogeneous structure and the variation in structure from one place to another is very large. There were also indications that the material around the central vertex axis of the iron pillar has a different structure than the material away from the axis. This work we also published in International Conference on Ultrasonics in '89. The study has led the way to understand how was it made in 1600 years back, and why does it not corrode. This is one of the artifact. Artifact is a device or a standard sample which is used to be a standard for intercomparison. Intercomparison in standards, you all may be knowing that is used for comparison of the results or comparison of the setup or comparison of the measurement parameter for a various lab. This in ultrasonic entity we have designed and developed this artifact for detection, location, and sizing of artificially developed holes, and we have circulated it to various labs through NABL. We have developed three similar blocks, NDT blocks, as in, and provide and given it to the NABL for piloting for the intercomparison or ultrasonic entity. This is the ultrasonic NDT artifact, and it is a steel blank is prepared. Ultrasonic testing of blank is made, designed and fabricated the artificial defect in it, and separators also designed and fabricated at NPL, welding of scanning plates and camouflage plate with separators, painting of plates, tamper-proof ultrasonic scanning of plates, and preparation of protocol is made. Usually, the block is sent to different test laboratories for locating and sizing of the defect with their own ultrasonic methods, and that result are received by the piloting laboratory here at NABL or at NNPL. Then the piloting laboratories take those results and compare the results, and if it becomes the capability of that test laboratory, if they have found the results competitive to the pilot within the associated uncertainty of the defects. So here are the number of defects located and sized by ultrasonic methods. These are the number of 8 defects, and it's their location. And what we see is that one is 15 mm, 11 mm, 8.5 mm, 18 mm. These all 8 defects are artificially developed in the artifact and then determined and located by ultrasonic methods. Now, ensuring better quality of rays. Also, we have worked on making reference rails. You may be knowing that world's longest 120-meter rails are now made in India at Jindal Steels, Raigad, Chhattisgarh. For safety and quality assurance, the rails are tested online at the manufacturing site by ultrasonic method. The calibration is done by using a reference standard. These are called test rails. These test rails have several holes and notches, and these earlier were
Participants are requested to kindly switch off their mic. It is requested to kindly switch off your mic, please. Pramod ji, Mr. Pramod, kindly switch off your mic. Mr. Pramod, kindly switch off your mic.
And notches.
Thank you. Oh, so sorry, sir. Please continue. Sorry.
Okay. Actually, these test rails are tested at site, at manufacturing site by using reference standard. These are called test rails. These test rails were procured from outside India, where from they have procured their ultrasonic test system. But in India, we at NPL, we help them and we advise them for design and developing of these test rails. They are fabricated in India by using Fijimec at Hyderabad, and maintenance of these test rails were made by these Jindal Steels, and the dimension accuracy, ultrasonic response were also measured by NPL to ensure the acceptable quality of the test rails. That means these test rails were designed and fabricated in India and then calibrated by NPL. And they are still in use at Jindal Steels at Raigad. So ultrasonic used that application for giving it that. This will conclude my talk. Measurement of ultrasonic velocity, attenuation, and power parameters are used for most applications in ultrasonics. Ultrasonics is a very important tool for material characterization, NDT, high power and low power applications. In NDT, flow detection, location, and sizing is possible online as well as in offline. It is highly accurate in determining the reflector position and estimating the size and shape of the flow. Thickness measurement of material with one side accessible by pulse echo technique can be easily measured. Sensitive to both surface and subsurface discontinuities or defects or flow size measurement. And minimal part preparation is required for most of the applications. Electronic equipment provides instantaneous results, and nowadays detailed image can be produced with automated systems. I will advise to my co-workers presented here. Work presented here is done as a teamwork at Ultrasonic Standards Group at NPL during my time. I sincerely acknowledge with thanks to Dr. Ashok Kumar, Dr. P.K. Dubey, Mrs. Rita Gupta, Mr. Ravinder Kumar, Dr. V.N. Bindal, and Dr. T.K. Saxena, Dr. J.N. Som, and Mr. Om Prakash for contributing to the work we carried out. So I think.
Thank you, sir. Thank you very much for this brief and wonderful presentation. I have received the information during this presentation that it was one of the wonderful and knowledgeable with clear concept presentation. Thank you very much, sir. Now I would like to request all the participants to kindly switch on their video and switch off their mics if they're not saying anything. And sir, kindly remove this PPT from the website. Thank you, sir. Thank you very much. Now my RSL and NIC team can take few photographs for our social media platforms. With this, I would like to thank Professor Dr. Yudhishthir Kumar, my NIC team, and all the participants to be with us. Certainly, these type of programs will be very helpful for the development of the standards in our country. These are the knowledgeable scientists who are working in this. Sir, I would like to request you to kindly continue and give us some more lectures on these very important topics. Thank you. Thank you very much. Thank you all. Thank you. Namaskar. Thank you.
Thank you.
Thank you, sir.
Thank you, Astaji.